For my project, I made a wood gasifier. In this case, an updraft gasifier. There are a couple of different designs of wood gasifiers. The FEMA document that we read described a downdraft gasifier, and the second type is a updraft gasifier. The updraft gasifier has a couple of disadvantages. Any tar that is generated inside the pyrolysis chamber will not be fully decomposed into gases. And so a downdraft gasifier, such as described by the FEMA document, would have an open top, and the tubing would actually pull the gases off of the bottom of the pyrolysis chamber. The downdraft version does require a negative pressure or vacuum generated by the engine to draw the gases out of the pyrolysis chamber and through the system. So cautions to note with a gasifier design such as this whole assembly is going to become extremely hot. In addition to that, we are making flammable gases, so any buildup of gases anywhere could possibly cause a fire or explosion. And third, the gases created by this system are toxic and the system should be used in a well-ventilated area. A simple updraft gasifier can be made with a fire chamber, a pyrolysis chamber, cooling tower assembly, water chamber, and a filter chamber, some valves, and an assortment of tubing. The fire chamber holds the combustible material to generate the heat. Inside the pyrolysis chamber is where the biomass is changed from wood pieces into several different components: tar, carbon dioxide, carbon monoxide, and small amounts of hydrogen. To understand how we are going to convert wood into a gas, we first need to cover the chemical composition of wood. To use the wood as a fuel, it needs to contain certain periodic elements. These elements we are concerned with are hydrogen, oxygen, and carbon. These are the elements that will form the flammable gases we need to operate the internal combustion engine. On the slide, you can see the chemical makeup of gasoline, diesel, biodiesel, and vegetable oil, and wood. Of these fuels, gasoline is the simplest, containing only 7 carbon atoms and 16 hydrogen atoms. Diesel is slightly more complex, adding a couple of carbon and hydrogen atoms. And then biodiesel is slightly more complex than diesel by adding an ester group of carbon and oxygen to the mix. Vegetable oil is very complex in that it has 3 hydrocarbon chains bonded together. None of these fuels hold a candle to the complexity that is the composition of wood. You can see on the screen that wood is composed of 3 major components: cellulose, lignin, and hemicellulose. Each of those substances have their own chemical compositions, and each one of those formulas is more complex than vegetable oil. But the periodic elements contained in the formulas are similar. All the fuels shown here contain carbon and hydrogen, and some of the fuels have that extra oxygen molecule added in. To use the wood as a fuel for an internal combustion engines, we need to break down the long chains of the chemical composition, break down those hydrogen and carbon molecules into more simple forms. We do that through pyrolysis. So what exactly is pyrolysis? Pyrolysis is the decomposition of biomass by heat. So inside that gasification chamber, several stages are going to occur. First is the drying stage. That's where moisture in the biomass is vaporized from the heat. That stage is going to occur between temperatures of 212 and 300 degrees Fahrenheit. Second is the pyrolysis stage. And this is where the biomass begins to be converted from a solid mass. So pyrolysis occurs in the absence of oxygen and turns the biomass into charcoal and gases. This stage occurs between 390 and 930 degrees Fahrenheit. So from that stage, we enter the combustion stage, and this is where that charcoal, tar gases, and water vapor combine and are heated to temperatures between 1500 and 1200 and 2200 degrees Fahrenheit. The charcoal becomes hot reactive charcoal, and the tar gases and water vapor combine into water vapor and carbon dioxide. The fourth stage is reduction. It's the final stage in the gasification process and occurs at temperatures between 1200 and 1600 degrees Fahrenheit. So this is where the water vapor, carbon dioxide, tar, and reactive charcoal combine to form hydrogen and carbon monoxide, are the flammable gases that we need to run our internal combustion engine. Prior to entering the engine, the gases from the pyrolysis chamber would ideally be cooled to about 70 degrees Fahrenheit. To begin this process, the gases come out of the pyrolysis chamber and into the cooling tower assembly. It's a simple copper tubing assembly that transfers heat to the air. We continue the cooling process where we have a coil of copper tubing submerged in water. In addition, in the water chamber, a chemical reaction occurs between carbon monoxide and the water, where carbon dioxide and hydrogen gases are formed. Inside the filter chamber, we want to try to clean out any of the remaining ash or tar that is not captured in the water. I've seen a couple of different variations on this. I've just taken some clean rags and stuffed them down intake line running to the bottom of the chamber. The gases will flow through the filter material and then come back out through the exit line. For the valve setup, I've got a 2 valve setup. I've got this exit to atmosphere, and this is where I'm going to testing the gas to see its flammability. So at the onset of the ignition of the fire and the generation of the gases, this valve will be open and venting the gases created to the atmosphere. At which point we are ready to attempt to start the engine. We will shut this valve and open this valve through this line directly to the engine intake system. Just like any fuel, there are some conditions that need to be maintained to run an internal combustion engine on wood gas. Two of these conditions are gas temperature at the intake and the air to fuel ratio. For maximum power, the gas needs to be kept at a certain temperature. That temperature for wood gas is around 70 degrees Fahrenheit. At that temperature, the gas is dense and very usable for an internal combustion engine. In the pyrolysis stages, we learned that the stages can be upwards of 2,000 degrees Fahrenheit. So to get down to that 70 degrees Fahrenheit, we are going to have to cool the gases considerably before they reach the engine. In fact, for every 10 degrees Fahrenheit that the gas is above 70 degrees Fahrenheit, we are going to lose roughly 10% of our engine's power output. The second condition that needs to be met is the air-fuel ratio. For a wood gas, the ideal condition is 1 unit of fuel to 1 unit of air. While this may seem very easy condition to achieve, the amount of airflow into the engine must be calculated and the gas flow regulated accordingly. We're going to begin our experiment. We are going to ignite the fuel outside of the pyrolysis chamber. We've taken some temperature readings and some measurements of the temperatures of different parts of the components to just keep track of how close we are getting to that ideal temperature of the exit gas being about 70 degrees Fahrenheit. So let's get going. We've got our fire going and increasing the temperature of the pyrolysis chamber. We saw some bubbles early off coming out of the water chamber. We think that was due to the increase in the pressure inside. We've not yet generated any gas.
You can see we've begun to generate some gas. You can see the bubbles being created there going through the water. If you look closely enough, you can also see the tar and ash being captured by the water.
You can see here one of my many attempts to ignite the gas that was being vented to the atmosphere. You can see the gases vented from the system were smoky in appearance. I believe that it was not smoke but water vapor. Moisture dripping from the vent was noticed several times. It did seem to affect the flammability of the gas. When little or no moisture was present, the gas was more easily ignited. When visible moisture was at the vent, the gas was more difficult to ignite. While the gases never burned for more than 2 or 3 seconds at a time, the system was able to generate flammable gas. Well, we've tried a couple of times to start the engine on the gas, but I've had no luck. Either the gases we're producing are too hot, or we can't get the air fuel mixture right for the engine. Throughout the experiment, temperature readings from several components of the gasifier were taken. I took temperature readings from the top of the pyrolysis chamber, the cooling tower, just before it entered the water chamber, the copper coil that was submerged in the water chamber, the filter material temperature, and the tip of the gas vent. I began the experiment at 8:25 and took initial readings of all components, and all the components at that time were of relatively similar temperature. After some final checks on the gasification system, I ignited the fuel in the combustion chamber and took temperature readings roughly every 5 or 10 minutes. At 8:52, the temperature had risen significantly on the top of the pyrolysis chamber and continued to do so for the rest of the test. In this test, it reached a maximum temperature of 450 degrees. It should be noted that no internal temperatures of the pyrolysis chamber were taken. I cannot be sure of the temperature that was achieved inside the chamber. Overall, most of the components continued to increase in temperature for the rest of the experiment. Due to variations in the method we used to take the readings, there were some fluctuations in the component temperatures. I would like to draw your attention to the cooling aspect of the system. I've previously stated that the ideal temperature for the wood gas is around 70 degrees Fahrenheit. You can see here that the cooling tower and water chamber had both exceeded this temperature within 30 minutes of starting the test. At 9:50 to 10 o'clock, there was a drastic increase in the temperature of the filter chamber. This was due to the water chamber bubbling over the exit port and hot liquid being passed into the filter chamber. It was also at 10 o'clock that the system began producing flammable gas inconsistently for the next 20 minutes. I want to leave you with some parting thoughts. While the gasifier I built was very simple and I was able to generate flammable gas with it, it had some major drawbacks. First, after I cooled the gasification chamber, I checked the wood level inside. At the beginning of the experiment, it was completely full of wood chunks. At the end of the experiment, there was less than 1 inch of ash and charcoal in the bottom. The chamber did an amazing job of converting the biomass into gas, but it also shows that the system was running out of fuel and was likely the reason I could not operate the engine on the gas. A larger gasification chamber would be needed to operate the system any longer than this test. Second, I hinted at this in the temperature readings. The cooling system was far too inadequate. At no point was the system able to generate flammable gas near the ideal temperature of 70 degrees Fahrenheit. Significant cooling system modification would be needed. And if I were to build a gasifier again, I would choose the downdraft gasifier type. While I would still need to address additional cooling needs, this system could be operated indefinitely as you are able to add fuel in from the top.